September 15th, 2025. A routine data review at the Green Bank Observatory in West Virginia reveals something that shouldn't exist. Deep within the electromagnetic noise surrounding Atlas, buried beneath the expected plasma frequencies and solar-wind interactions, sits a signal that refuses to behave like natural radio emissions should. The initial detection came not from targeted observation, but from automated monitoring systems designed to track radio interference from passing objects. Green Bank maintains constant vigilance over multiple frequency bands, cataloging the electromagnetic signatures of everything from geomagnetic storms to satellite transmissions. Atlas had been on the watch list since its discovery in July, logged as a potential source of standard cometary radio emissions caused by ionized gas interactions with the solar wind. What the algorithms flagged that Tuesday morning was different. Not the broad spectrum hiss of plasma turbulence, not the sporadic bursts of solar-driven ionization. Something regular, something structured, something transmitting from inside the comet's nucleus at a frequency that made no geological or chemical sense for a ball of ice and rock tumbling through space. The signal operates in the upper VHF band, specifically around 164 megahertz. This frequency sits in a relatively quiet region of the electromagnetic spectrum, above the chaos of Earth's ionosphere, but below the noise floor of most galactic background radiation. For a natural object to produce coherent emissions at this specific frequency requires mechanisms that standard comet physics simply doesn't provide. Initial pulse analysis revealed timing patterns that resist random interpretation. The signal repeats every 11.3 seconds with microsecond precision. Natural radio sources, like pulsars, maintain regular timing through rotational mechanics. Massive neutron stars spinning with clockwork regularity. But comets don't spin with such precision. They tumble chaotically, their rotation rates varying as outgassing jets push unevenly against their irregular surfaces. The frequency stability presents another puzzle. Natural radio emissions from comets typically drift across wide bandwidths as plasma conditions change and magnetic fields fluctuate. Atlas's signal maintains its central frequency with less than 0.01% deviation, the kind of stability that requires either impossible natural coincidence or active frequency control through mechanisms that shouldn't exist in a comet nucleus. Power calculations compound the mystery. Based on the signal strength detected at Earth and accounting for inverse square losses across the distance, Atlas appears to be radiating approximately 10 kilowatts of electromagnetic energy in this narrow frequency band. For comparison, typical natural radio emissions from comets measure in milliwatts at best. The energy budget required to sustain this broadcast exceeds anything that passive chemical or thermal processes should produce. Green Bank operators ran every diagnostic protocol designed to identify false positives. Radio frequency interference from terrestrial sources, satellite cross-contamination, instrumental artifacts created by receiver electronics, processing errors in the signal chain. Each test returned negative. The signal was real, extraterrestrial in origin, and emanating from the precise coordinates where Atlas's nucleus should be located within its massive carbon dioxide envelope. By September 17th, 2 additional facilities had independently confirmed the detection. The Parkes Radio Telescope in Australia picked up identical pulse characteristics during its overnight observing window. The Allen Telescope Array in California part of the SETI Institute's ongoing sky survey, had actually been recording the signal since early September, but hadn't flagged it for review until Green Bank's alert prompted retroactive data analysis. 3 independent detections using different receiver systems, different geographic locations, and different analysis pipelines all converged on the same conclusion. Atlas was broadcasting something that comets aren't supposed to broadcast. The question that nobody wanted to ask out loud, but everyone was thinking, became unavoidable. What if we've been classifying Atlas as a natural object when the evidence has been suggesting otherwise all along? The signal's discovery explained something that had been bothering observers since August. Atlas's unprecedented behavior, its massive carbon dioxide coma, its impossible anti-tail structure, its brightness anomalies, all might represent not mysterious natural processes, but controlled artificial systems operating under principles we don't understand. And now, those systems were apparently talking, whether to us, to something else, or simply maintaining internal communications between components of a larger mechanism remained terrifyingly unclear. The electromagnetic signature emanating from Atlas defies every template in the radio astronomy textbook. When researchers first isolated the signal from background noise, what emerged wasn't the chaotic static of natural cosmic radio sources, but something that looked disturbingly organized when plotted on spectrographic displays. The primary carrier wave sits at 164.37 megahertz, maintaining frequency stability that requires explanation. Natural radio sources drift and wander across the spectrum as their physical conditions change. Pulsars shift frequency due to interstellar medium dispersion. Solar radio bursts sweep across gigahertz ranges in seconds. Jupiter's decametric emissions dance wildly across tens of megahertz as its magnetic field rotates. Atlas does none of this. Its carrier frequency holds steady within measurement precision, as if locked to some internal reference that refuses to vary despite the comet's tumbling motion and changing solar environment. The pulse structure reveals even stranger characteristics. Every 11.3 seconds, the signal intensity increases by approximately 40% above baseline for exactly 0.8 seconds before returning to its nominal level. This creates a distinctive sawtooth pattern on intensity plots, rising sharply and falling gradually in a shape that suggests controlled modulation rather than random fluctuation. Between these primary pulses, secondary variations appear at irregular intervals, sometimes clustered together, sometimes separated by multiple primary pulse cycles. Bandwidth analysis shows the signal occupies approximately 15 kHz of spectrum, narrow enough to suggest artificial generation, but wide enough to carry significant information density if the variations represent data encoding. For comparison, AM radio stations on Earth typically occupy 10 kHz of bandwidth, while natural astronomical masses might span megahertz-wide ranges. Atlas sits precisely in the middle, too focused for chaos, too broad for simple carrier transmission. The polarization characteristics add another layer of mystery. Radio waves can oscillate in various orientations, and natural sources typically produce unpolarized or randomly polarized emissions. Atlas's signal shows circular polarization that alternates between right-handed and left-handed states in patterns that correlate with the secondary pulse variations. This switching behavior resembles phase shift keying, a modulation technique used in human-designed communication systems to encode digital information. Spectral analysis revealed additional structure buried in what initially appeared to be noise surrounding the main carrier. Harmonic frequencies appear at exact integer multiples of the fundamental, creating a comb-like pattern across the spectrum. These harmonics shouldn't exist in natural radio emissions from comets, which lack the coherent oscillating structures needed to generate such mathematically precise frequency relationships. Time frequency analysis exposed something even more intriguing. When researchers plotted how the signal's characteristics change over observation periods spanning hours, recurring patterns emerged that operate on multiple timescales simultaneously. Fast variations happening over milliseconds nest within slower modulations spanning seconds, which themselves sit within minute-scale trends. This hierarchical timing structure mirrors the kind of multiplexed signaling used in complex communication protocols, where different information streams share the same carrier. The signal's power output calculation produces numbers that challenge conventional comet energetics. To generate the observed field strength at Earth requires ATLAS to radiate roughly 10 kilowatts in this narrow frequency band alone. Natural radio emissions from comets barely register above instrument noise floors. The mechanism producing ATLAS's broadcast would need dedicated power generation orders of magnitude beyond anything sublimating ice and outgassing volatiles could provide through chemical energy alone. What we heard from ATLAS wasn't the random electromagnetic whisper of dead rock and frozen gas. It was something that looked, sounded, and mathematically behaved like engineered transmission. And that changed everything. The signal had been broadcasting for weeks before anyone realized what they were looking at. Reconstruction of archived data from multiple observatories painted a troubling picture of how close humanity came to missing the discovery entirely, and raised uncomfortable questions about what else might have been overlooked during ATLAS's approach through the inner solar system. The earliest confirmed detection now traces back to August 28, 2025, captured by the Allen Telescope Array during routine sky survey operations. The facility's automated systems recorded the emissions, but classified them as potential radio frequency interference, flagging the data for later review that might never have happened without subsequent events forcing retroactive analysis. For 18 days, the signal sat unexamined in digital archives, while ATLAS continued its approach toward Mars. Parkes Radio Telescope in Australia independently detected the emissions on September 6th during scheduled observations of the southern sky. Again, initial classification marked the signal as terrestrial interference, this time suspected to originate from passing satellites whose orbital paths happened to intersect the telescope's pointing direction. The geographic separation between Parkes and Allen should have immediately suggested extraterrestrial origin, but institutional silos prevented cross-facility data sharing until much later. Green Bank Observatory achieved the breakthrough on September 15th, not through superior instruments, but through human curiosity. A routine review of electromagnetic monitoring data surrounding known solar system objects included ATLAS in the sweep. Unlike the automated systems that had dismissed previous detections, human analysis recognized patterns that demanded explanation. Within hours, Green Bank operators were coordinating with other facilities to confirm the signal's extraterrestrial nature. The coordination revealed something disturbing. When facilities compared their archived observations, the signal appeared to have intensified significantly between late August and mid-September. Early detections from Allen showed signal strength barely above noise thresholds. By the time Green Bank made its discovery, Atlas was broadcasting at nearly triple the initial power levels. This evolution suggested either the source was approaching some kind of activation threshold, or observers were finally detecting emissions that had been present but too weak to register during Atlas's more distant approach. September 17th brought confirmations from Parkes and Allen after their teams reviewed archived data prompted by Green Bank's alert. The Arecibo Observatory in Puerto Rico, despite its damaged state after the 2020 collapse, maintained limited receiving capabilities and confirmed detection using surviving instruments. Within 48 hours, 5 major radio astronomy facilities had verified the signal's existence and extraterrestrial origin. What nobody discussed publicly was the gap. Atlas had been discovered on July 1st. Radio telescopes had been occasionally observing the object since mid-July as part of standard comet monitoring programs. Yet, the first archived detection dated to late August. Either the signal began transmitting sometime between July and August, or earlier emissions were too weak to detect, or someone had detected them and chosen not to share. Military and intelligence agencies maintain classified space surveillance networks with capabilities exceeding civilian radio astronomy. These systems track everything from satellites to space debris with resolution and sensitivity that remain carefully guarded secrets. Did classified sensors detect Atlas's signal weeks or months before civilian observatories? Were there discussions at security-cleared levels about the implications while the public remained unaware? The detection timeline suggested 2 equally troubling possibilities. Either humanity's radio astronomy infrastructure nearly missed the most significant signal detection in history through institutional inertia and data classification protocols, or someone knew much earlier and maintained deliberate silence while the scientific community stumbled toward independent discovery. Comets aren't supposed to have internal power sources. This fundamental principle underlies everything astronomers thought they understood about these ancient travelers from the outer solar system. A comet is supposed to be little more than a dirty snowball, frozen volatiles, and embedded rock that sublimates when solar heating warms its surface. The energy available to any natural comet comes entirely from external sources, primarily the sun's radiation driving chemical and physical processes that require no internal generation. Atlas's signal shatters this framework completely. The 10 kilowatt continuous broadcast detected from its nucleus demands an energy source that chemistry alone cannot provide. Sublimating water ice releases approximately 2.6 megajoules per kilogram. Carbon dioxide sublimation offers even less. To generate 10 kilowatts continuously, Atlas would need to sublimate roughly 4 kilograms of material every second, converting that thermal energy into electromagnetic radiation with perfect efficiency, a physical impossibility that violates thermodynamic principles. The frequency selection compounds the impossibility. Natural radio emissions from comets occur when solar wind particles interact with the expanding coma, creating plasma, instabilities that generate broadband electromagnetic noise. These emissions typically concentrate in the lower frequency ranges where plasma physics naturally operates, below 30 megahertz. Atlas broadcasts at 164 megahertz, a frequency that requires coherent oscillating structures, rather than chaotic plasma interactions. Consider what generating a stable carrier wave at this frequency actually requires. On Earth, radio transmitters use electronic oscillators, precisely tuned circuits that convert electrical power into electromagnetic radiation at specific frequencies. Natural astronomical masers can produce coherent radio emissions through quantum mechanical processes in excited molecules. But these require specific environmental conditions and produce entirely different spectral signatures than what ATLAS displays. The signal's stability over multiple observation sessions separated by days reveals another impossibility for natural explanations. Comets tumble unpredictably as asymmetric outgassing creates random torques. Their rotation rates vary continuously. Any radio emission mechanism tied to the comet's physical structure should show corresponding frequency variations as Doppler shifts from the changing rotation. ATLAS's signal shows no such variation. The frequency remains locked, as if generated by a source that either doesn't rotate with the nucleus or actively compensates for rotational effects through frequency stabilization impossible in natural systems. The timing precision of the 11.3 second pulse repetition creates problems that natural models cannot address. Achieving microsecond level timing, accuracy over extended periods, requires either impossible mechanical precision in a rotating irregular body, or active timekeeping through processes that shouldn't exist in frozen volatiles and embedded silicates. No known natural phenomenon produces such regularity without invoking neutron star physics, and ATLAS clearly isn't a neutron star hiding inside a comet disguise. The hierarchical modulation structure detected in the signal's fine details suggests information encoding at multiple timescales simultaneously. Natural processes produce patterns, but they don't typically nest multiple periodic variations within each other in ways that maximize information density within available bandwidth. This looks like engineered communication protocol design, rather than accidental physics. What changes everything isn't just that ATLAS produces radio emissions. Natural objects produce radio emissions all the time. What changes everything is that ATLAS produces radio emissions that look designed, that require power generation mechanisms beyond chemistry, that maintain precision impossible for tumbling rocks, and that display characteristics matching engineered systems rather than natural chaos. If ATLAS isn't natural, then everything observed since July takes on terrifying new meaning. 1974 marked a pivotal moment in humanity's relationship with the cosmos, when the Arecibo Observatory broadcast a message toward the globular star cluster Messier 13. The transmission lasted less than 3 minutes, but represented our species' first deliberate attempt to announce our presence to potential listeners among the stars. That message traveled at light speed toward its destination 25,000 light-years away, and any response wouldn't arrive for 50,000 years minimum. The act itself mattered more than any expectation of reply. The Arecibo message contained 1,679 binary digits, arranged to form a pictogram when decoded properly. Information about human DNA structure, Earth's population, our solar system's layout, and a representation of the radio telescope itself traveled outward at the speed of light. The exercise taught radio astronomers important lessons about signal design, information encoding, and the challenges of creating messages comprehensible to unknown recipients with unknown cognitive frameworks. Arecibo also spent decades listening, not just broadcasting. The facility's sensitive receivers monitored the sky for signals that might indicate technological civilizations operating beyond Earth. The search for extraterrestrial intelligence used Arecibo's capabilities to scan millions of star systems across thousands of hours of observation time. The protocols developed for distinguishing artificial signals from natural radio sources established standards that the entire SETI community adopted for identifying potential contact events. Those protocols specified clear criteria for artificial signals. Narrow bandwidth transmissions indicate technological origin because natural astrophysical masers typically produce much broader spectral features. Frequency drift patterns that compensate for relative motion between source and observer suggest deliberate targeting rather than accidental emission. Modulation structures carrying information. Density beyond random noise point toward engineered communication rather than natural chaos. Atlas's signal meets every single criterion that Arecibo protocols established for identifying artificial transmissions. The narrow 15 kHz bandwidth sits precisely in the range that SETI researchers consider optimal for interstellar communication. The frequency stability suggests active compensation for motion effects. The hierarchical modulation structure indicates intentional information encoding. By the standards radio astronomers developed for identifying extraterrestrial intelligence, Atlas qualifies unambiguously as an artificial source. But Arecibo protocols assumed signals would originate from distant star systems, not from objects already inside our solar system. The psychological and procedural frameworks for handling detection events presumed humanity would have years or decades to analyze signals arriving from light years away. Time for verification, time for international coordination, time for careful consideration of response options. Atlas provides none of this comfortable distance. The source sits mere light minutes away and approaches closer every day. The precedent Arecibo established creates an uncomfortable paradox for current observations. If Atlas's signal originated from Alpha Centauri or any other nearby star system, SETI protocols would demand immediate public announcement and international scientific collaboration for analysis and potential response. The signal's characteristics would trigger established contact procedures developed over decades of preparation for this exact scenario. Yet because the source masquerades as a comet rather than announcing itself as a distant civilization, institutional responses have been confused, hesitant, and seemingly coordinated toward silence rather than disclosure. Arecibo itself sits damaged and partially collapsed after structural failures in 2020 destroyed much of the facility's functionality. The symbolism cuts deep. Humanity's most famous tool for announcing ourselves to the cosmos and listening for replies now lies broken precisely when the most significant potential contact event in history demands every available receiver pointed toward the source. Whether Atlas's timing represents coincidence or something more calculated remains an open and deeply unsettling question. Comets do produce radio emissions through well-understood physical processes that require no exotic explanations or artificial mechanisms. Understanding these natural sources becomes crucial for evaluating whether Atlas's signal represents genuinely anomalous phenomena or simply unusual but explicable physics operating under conditions astronomers haven't previously encountered. The primary natural radio source from comets comes from plasma interactions between the solar wind and the expanding coma. As charged particles from the Sun collide with neutral gas molecules sublimating from the comet's surface, ionization creates a plasma environment surrounding the nucleus. This plasma can support various wave modes and instabilities that generate electromagnetic radiation across broad frequency ranges, typically concentrated below 30 megahertz, where plasma frequencies naturally resonate. Langmuir waves represent one common mechanism for radio generation in cometary plasmas. These electron oscillations produce emissions near the local plasma frequency, which depends on electron density in the coma. As the comet approaches the Sun and outgassing intensifies, plasma density increases and Langmuir wave frequencies shift accordingly. Observations of multiple comets have confirmed this behavior, with radio emissions tracking predicted plasma conditions as objects move through different solar distances. Type 2O and Type 3 solar radio bursts occasionally interact with cometary environments to produce secondary emissions. When coronal mass ejections or solar flares send shockwaves and particle beams through the inner solar system, comets positioned in these streams can act as scattering centers that modify and re-radiate the solar radio emissions. These events create sporadic radio signatures from comets that can briefly intensify before fading as the solar disturbance passes. Ion cyclotron waves provide another natural mechanism for electromagnetic generation near comets. Charged particles spiraling in magnetic fields produce characteristic frequencies determined by the particle mass and field strength. Water group ions dominating most cometary comas generate cyclotron emissions in predictable frequency ranges based on the embedded solar wind magnetic field. Multiple spacecraft missions have directly measured these waves in situ during comet flybys, confirming theoretical predictions. All these natural mechanisms share common characteristics that distinguish them from ATLAS's observed signal. Natural cometary radio emissions show broad spectral distributions spanning megahertz or more in bandwidth, rather than narrow, concentrated bands. The emissions vary chaotically as plasma conditions fluctuate with changing outgassing rates, solar wind properties, and magnetic field orientations. No natural mechanism produces the frequency stability, narrow bandwidth, or timing precision that ATLAS displays. The power levels present another distinguishing factor. Natural plasma emissions from comets typically measure in milliwatts when detected at Earth, barely registering above instrument noise floors. Even during the most intense outgassing events near perihelion, natural radio power remains orders of magnitude below what ATLAS continuously broadcasts. The energy conversion efficiency required to transform thermal sublimation energy into coherent electromagnetic radiation at observed power levels exceeds anything natural plasma physics can achieve. Spatial structure provides additional discrimination between natural and artificial sources. Plasma emissions originate from extended regions throughout the coma where solar wind interactions occur. This produces radio sources with angular sizes matching the coma's physical extent. ATLAS's signal appears to originate from a point source coincident with the nucleus location, suggesting generation within the solid body rather than the surrounding plasma environment. Natural radio sources in comets are real, well-studied, and completely insufficient to explain what observers are detecting from ATLAS. The mechanisms that should produce weak, broadband, chaotic emissions somehow generate strong, narrow-band, structured transmissions that look nothing like the physics textbooks predict. Either comet science is fundamentally wrong, or ATLAS isn't actually a comet. When researchers began applying information theory frameworks to Atlas's signal, the results produced numbers that shouldn't emerge from random natural processes. Mathematical analysis of the pulse structures, frequency variations, and timing relationships revealed layers of organization that resist dismissal as mere coincidence, or observer bias projecting patterns onto noise. Shannon entropy measurements quantify the information content within any signal by calculating how predictable or random the data stream appears. Pure random noise produces maximum entropy because every bit is unpredictable from previous bits. Highly ordered repetitive patterns produce minimum entropy because future bits become entirely predictable once the pattern is recognized. Atlas's signal sits precisely between these extremes, displaying entropy values characteristic of compressed data where redundancy has been removed. But information content remains high. The 11.3 second primary pulse interval shows stability that extends across thousands of repetitions observed over multiple weeks. Statistical analysis reveals timing variations of less than 10 microseconds, a precision level that requires explanation. Natural periodic phenomena like pulsar rotation achieve such precision through enormous rotational inertia that resists perturbation. A comet nucleus tumbling through space while venting gas asymmetrically should show timing variations, orders of magnitude larger than what Atlas displays. Fourier analysis of the secondary pulse patterns revealed frequency components that form harmonic relationships with the primary interval. Peaks appear at integer fractions and multiples of the fundamental 11.3 second period, creating a frequency comb structure typically associated with phase-locked systems. Natural processes rarely produce such mathematically precise harmonic relationships unless underlying resonant structures enforce the coupling. The polarization switching behavior shows correlation with secondary pulse timing that exceeds what random chance would produce. When researchers calculated the mutual information between polarization state changes and pulse intensity variations, the result indicated approximately 3.7 bits of shared information per switching event. This means that knowing the polarization state provides significant predictive power about upcoming pulse patterns, suggesting the two phenomena are coupled through common underlying mechanisms rather than occurring independently. Autocorrelation analysis exposed long-range structure extending across observation periods spanning hours. The signal shows periodicities nested within periodicities, with slower modulations at scales of minutes containing faster variations at scales of seconds and milliseconds. This hierarchical timing organization maximizes information density within available bandwidth, a design principle used in engineered communication systems but rarely observed in natural electromagnetic sources. The frequency stability analysis produced perhaps the most troubling results. After compensating for Doppler shifts from Earth's motion and Atlas's trajectory, the carrier frequency remains constant to within 0.003% across all observation sessions. Achieving this stability requires either a frequency reference more stable than atomic clocks, or active feedback systems that compensate for environmental perturbations. Neither option fits comfortably within natural comet physics. Researchers attempted to match Atlas's signal characteristics against every known class of natural radio emitter. Pulsar timing patterns show different statistical properties in their period derivatives. Stellar flare emissions display different spectral evolution. Planetary magnetospheric sources produce different modulation structures. Maser emission from excited molecules shows different bandwidth characteristics. No natural source category provides adequate match to the observed signal properties. The pattern analysis revealed something that made professional skeptics uncomfortable. When you calculate the probability that random natural processes would produce all the observed characteristics simultaneously through pure coincidence, the numbers become vanishingly small. Narrow bandwidth, precise timing, harmonic structure, stable frequency, hierarchical modulation, and polarization correlation would each individually strain natural explanations. Together, they create a profile that looks deliberately engineered rather than accidentally generated. The mathematics doesn't prove artificial origin, but it makes natural alternatives increasingly difficult to defend with straight faces. The global radio astronomy community maintains dozens of sensitive receiving facilities capable of detecting Atlas's signal. Yet public confirmations have emerged from only a handful of observatories, while others maintain conspicuous silence. This selective disclosure pattern raises questions about institutional coordination and what additional observations might exist in classified or unpublished form. The Very Large Array in New Mexico possesses capabilities far exceeding the facilities that made initial detections. Its 27-dish interferometric system can resolve signal directionality and source structure with precision that single-dish telescopes cannot match. The VLA observes Atlas's position in the sky regularly as part of routine survey operations. Yet no public data, releases, or scientific papers from VLA teams have addressed the electromagnetic emissions, despite the array being perfectly positioned and equipped to contribute definitive observations. LOFAR, the low-frequency array distributed across Europe, monitors radio sky continuously across frequencies that overlap Atlas's emission band. The facility's design specifically targets transient and variable radio sources, making it ideal for tracking signal evolution over time. Multiple LOFAR stations have direct line of sight to Atlas during various observation windows. The absence of public LOFAR data about the signal feels deliberate rather than coincidental, given the array's scientific mandate. China's 500-meter aperture spherical telescope, the world's largest single-dish radio telescope, remains notably silent about Atlas observations, despite capabilities that should make signal detection trivial. FAST's enormous collecting area provides sensitivity exceeding any Western facility. Chinese space science has been increasingly vocal about discoveries and achievements in recent years. The silence, specifically regarding Atlas's electromagnetic emissions, stands out against this pattern of active international scientific engagement. The Murchison Wide Field Array in Australia operates in the frequency range where Atlas broadcasts and maintains continuous monitoring of the southern sky. Its wide field of view and sensitivity to transient phenomena make it particularly suited for tracking variable sources like Atlas's signal. Australian radio astronomy traditionally shares data openly with international partners. The lack of MWA papers or press releases about Atlas creates an information gap that feels inconsistent with standard scientific practice. Russia's Ratan 600 radio telescope possesses unique capabilities for studying compact radio sources and has tracked numerous comets throughout its operational history. Russian astronomical institutions typically publish findings in international journals and participate actively in global scientific discourse. The absence of Rotan observations in the published literature about Atlas suggests either the facility hasn't observed the object, an unlikely scenario given its scientific interest, or observations exist but remain unpublished for unstated reasons. September 15th, 2025. A routine data review at the Green Bank Observatory in West Virginia reveals something that shouldn't exist. Deep within the electromagnetic noise surrounding Atlas, buried beneath the expected plasma frequencies and solar-wind interactions, sits a signal that refuses to behave like natural radio emissions should. The initial detection came not from targeted observation, but from automated monitoring systems designed to track radio interference from passing objects. What the algorithms flagged that Tuesday morning was different. Not the broad spectrum hiss of plasma turbulence, not the sporadic bursts of solar-driven ionization. Something regular, something structured, something transmitting from inside the comet's nucleus at a frequency that made no geological or chemical sense for a ball of ice and rock tumbling through space. The signal operates in the upper VHF band, specifically around 164 megahertz. This frequency sits in a relatively quiet region of the electromagnetic spectrum, above the chaos of Earth's ionosphere, but below the noise floor of most galactic background radiation. For a natural object to produce coherent emissions at this specific frequency requires mechanisms that standard comet physics simply doesn't provide. Initial pulse analysis revealed timing patterns that resist random interpretation. The signal repeats every 11.3 seconds with microsecond precision. Natural radio sources, like pulsars, maintain regular timing through rotational mechanics. Massive neutron stars spinning with clockwork regularity. But comets don't spin with such precision. They tumble chaotically, their rotation rates varying as outgassing jets push unevenly against their irregular surfaces. The frequency stability presents another puzzle. Natural radio emissions from comets typically drift across wide bandwidths as plasma conditions change and magnetic fields fluctuate. Atlas's signal maintains its central frequency with less than 0.01% deviation, the kind of stability that requires either impossible natural coincidence or active frequency control through mechanisms that shouldn't exist in a comet nucleus. Power calculations compound the mystery based on the signal strength detected at Earth and accounting for inverse square losses across the distance. Atlas appears to be radiating approximately 10 kilowatts of electromagnetic energy in this narrow frequency band. For comparison, typical natural radio emissions from comets measure in milliwatts at best. The energy budget required to sustain this broadcast exceeds anything that passive chemical or thermal processes should produce. By September 17th, 2 additional facilities had independently confirmed the detection. The Parkes Radio Telescope in Australia picked up identical pulse characteristics during its overnight observing window. The Allen Telescope Array in California, part of the SETI Institute's ongoing sky survey, had actually been recording the signal since early September, but hadn't flagged it for review until Green Bank's alert prompted retroactive data analysis. The electromagnetic signature emanating from Atlas defies every template in the radio astronomy textbook. When researchers first isolated the signal from background noise, what emerged wasn't the chaotic static of natural cosmic radio sources, but something that looked disturbingly organized when plotted on spectrographic displays. The primary carrier wave sits at 164.37 megahertz, maintaining frequency stability that requires explanation. Natural radio sources drift and wander across the spectrum as their physical conditions change. Pulsars shift frequency due to interstellar medium dispersion. Solar radio bursts sweep across gigahertz ranges in seconds. Jupiter's decametric emissions dance wildly across tens of megahertz as its magnetic field rotates. Atlas does none of this. The pulse structure reveals even stranger characteristics. Every 11.3 seconds, the signal intensity increases by approximately 40% above baseline for exactly 0.8 seconds before returning to its nominal level. This creates a distinctive sawtooth pattern on intensity plots, rising sharply and falling gradually in a shape that suggests controlled modulation rather than random fluctuation. Bandwidth analysis shows the signal occupies approximately 15 kilohertz of spectrum, narrow enough to suggest artificial generation, but wide enough to carry significant information density if the variations represent data encoding. The polarization characteristics add another layer of mystery. Radio waves can oscillate in various orientations, and natural sources typically produce unpolarized or randomly polarized emissions. Atlas's signal shows circular polarization that alternates between right-handed and left-handed states in patterns that correlate with the secondary pulse variations. The signal had been broadcasting for weeks before anyone realized what they were looking at. Reconstruction of archived data from multiple observatories painted a troubling picture of how close humanity came to missing the discovery entirely. The earliest confirmed detection now traces back to August 28, 2025, captured by the Allen Telescope Array during routine sky survey operations. For 18 days, the signal sat unexamined in digital archives, while Atlas continued its approach toward Mars. Parkes Radio Telescope in Australia independently detected the emissions on September 6th during scheduled observations of the southern sky. Again, initial classification marked the signal as terrestrial interference. Green Bank Observatory achieved the breakthrough on September 15th through human curiosity, rather than automated systems. The coordination revealed something disturbing. When facilities compared their archived observations, the signal appeared to have intensified significantly between late August and mid-September. This evolution suggested either the source was approaching some kind of activation threshold, or observers were finally detecting emissions that had been present but too weak to register during Atlas's more distant approach. Comets aren't supposed to have internal power sources. This fundamental principle underlies everything astronomers thought they understood about these ancient travelers from the outer solar system. A comet is supposed to be little more than a dirty snowball, frozen volatiles, and embedded rock that sublimates when solar heating warms its surface. Atlas's signal shatters this framework completely. The 10 kilowatt continuous broadcast detected from its nucleus demands an energy source that chemistry alone cannot provide. Sublimating water ice releases approximately 2.6 megajoules per kilogram. To generate 10 kilowatts continuously, Atlas would need to sublimate roughly 4 kilograms of material every second, converting that thermal energy into electromagnetic radiation with perfect efficiency, a physical impossibility. The frequency selection compounds the impossibility. Natural radio emissions from comets occur when solar wind particles interact with the expanding coma, creating plasma instabilities that generate broadband electromagnetic noise. Atlas broadcasts at 164 megahertz, a frequency that requires coherent oscillating structures rather than chaotic plasma interactions. 164.37 megahertz occupies a peculiar position in the electromagnetic spectrum that seems almost deliberately chosen for interstellar communication. This frequency sits in what radio astronomers call the water hole, a relatively quiet region between the spectral lines of hydrogen and hydroxyl. The symbolism hasn't escaped notice. Water being hydrogen plus hydroxyl, the fundamental molecule for life as we understand it. The frequency choice becomes even more intriguing when considering Atlas's massive carbon dioxide envelope. Radio waves at different frequencies interact differently with matter depending on physical and chemical properties. 164 megahertz represents an optimal compromise for penetrating Atlas's unprecedented coma while remaining detectable across interstellar distances. The frequency stability observed across all detection sessions suggests active compensation for Doppler effects caused by Atlas's motion. As the comet moves through space at approximately 40 kilometers per second relative to the Sun, naive radio emissions should show frequency shifts of roughly 22 kilohertz. Yet the observed signal maintains its central frequency with minimal drift, requiring mechanisms that shouldn't exist in natural comet nuclei. Amateur radio astronomy networks operating worldwide provide independent verification capabilities outside institutional control. Online forums show scattered reports of Atlas signal detection, with observers using modest dish antennas confirming they could detect periodic enhancements when pointing toward Atlas's coordinates. Software-defined radio enthusiasts applied their own signal processing techniques, independently confirming the 11.3 second pulse interval and frequency stability. However, the pattern suggests that far more institutions have detected and characterized Atlas's signal than have chosen to discuss it publicly. The Deep Space Network facilities possess receiving capabilities that dwarf civilian radio telescopes. Atlas's 10 kilowatt emission would register clearly on DSN receivers. Yet no acknowledgement appears in any publicly accessible documentation. Military space surveillance networks maintain continuous watch over everything moving through near-Earth space using classified sensor capabilities. The United States Space Force operates the Space Surveillance Network, tracking objects with resolution exceeding civilian facilities. Russian and Chinese systems maintain similar capabilities. The timing raises uncomfortable questions about whether classified sensors observed the signal months before civilian discovery. NASA's official position on Atlas remains frustratingly vague, despite extensive observation capabilities. Press releases emphasize trajectory and physical characteristics, while carefully avoiding any mention of electromagnetic emissions. The European Space Agency follows a similar pattern, maintaining complete silence about radio observations. This coordinated institutional quiet feels deliberate rather than coincidental. When Oumuamua tumbled through the inner solar system in 2017, its extreme elongation and unusual acceleration sparked debate about artificial origins. No radio observations detected artificial signals, though the object was observed after perihelion when it was rapidly receding. Atlas benefits from earlier detection and more extensive monitoring, providing opportunities that Oumuamua's brief visibility never offered. If Atlas transmits meaningful information, the content might reveal intentions and origins that transform humanity's understanding. The simplest message would be cosmic identification, broadcasting basic information about creators and location. More sophisticated messages might include warnings or observational data. The possibility of hostile intent cannot be dismissed. Perhaps most unsettling is that the message might address humanity directly, demonstrating impossible knowledge of Earth. The silence from space agencies about message content speaks volumes. Mundane greetings would likely be shared openly. Complex or troubling messages might justify the careful information management witnessed. Until transparency replaces silence, Atlas's message remains the most significant unknown in a discovery already defined by mysteries that challenge everything we thought we knew about interstellar visitors and our place in the cosmos. But the comparison reveals something troubling when examining observation timelines and capabilities. Oumuamua's radio observations occurred after the object had already passed perihelion and was rapidly receding from the inner solar system. By the time targeted searches began, the object was beyond 1 astronomical unit from Earth and fading quickly. Sensitivity calculations suggest that a signal with Atlas's characteristics, 10 kilowatts transmitted from Oumuamua's distance during observation windows, might have fallen below detection thresholds given the integration times and frequencies monitored. Atlas benefits from earlier detection and more extensive monitoring during its approach. The object was identified in July while still relatively distant, allowing months of observation before its closest approaches. This extended baseline provides opportunities that Oumuamua's brief visibility window never offered. If Oumuamua had broadcast similar signals, limited observation windows and suboptimal timing might have caused observers to miss them entirely. The morphological differences between the objects complicate direct comparison. Oumuamua showed no detectable coma or extended atmosphere, appearing as a bare, rocky or icy body. Atlas displays an unprecedented carbon dioxide envelope extending hundreds of thousands of kilometers. If both objects represent similar technological artifacts, their different operational modes might reflect different mission profiles or stages of activation. Both objects arrived on hyperbolic trajectories originating from interstellar space, distinguishing them from solar system natives bound gravitationally to the Sun. Both displayed characteristics that challenged conventional understanding of natural bodies. Both generated intense scientific interest, followed by institutional caution about extraordinary claims. The pattern suggests that interstellar visitors may routinely display anomalies that resist easy categorization. The key question becomes whether astronomers learned the wrong lessons from Oumuamua. Perhaps the null radio results were interpreted as proof of natural origin when they actually reflected insufficient sensitivity or unfortunate observation timing. If Oumuamua was broadcasting and nobody heard because we weren't listening carefully enough or at the right times, then Atlas represents a second chance that we cannot afford to waste through institutional hesitation or incomplete observation campaigns. The most tantalizing and frustrating aspect of Atlas's signal centers on whether the observed modulation patterns carry encoded information or merely represent the electromagnetic equivalent of engine noise from unknown physical processes. Distinguishing between meaningful data transmission and meaningless but structured emissions requires analysis techniques that push the boundaries of information theory and pattern recognition. Initial attempts to decode the signal applied standard communication protocols used in terrestrial radio systems. Amplitude modulation, frequency modulation, and phase shift keying analysis revealed structure but no obvious message content that mapped to known encoding schemes. The signal resists interpretation through frameworks designed for human-generated communications, suggesting either fundamentally alien encoding methods or natural processes that coincidentally mimic artificial modulation. Researchers applied compression detection algorithms that identify statistical signatures of information content regardless of specific encoding details. Truly random noise shows high entropy with no patterns. Highly compressed data also appears random because redundancy has been removed through efficient encoding. Uncompressed messages show intermediate entropy with visible structure. Atlas's signal displays characteristics most consistent with compressed data, showing high entropy with subtle correlations that suggest underlying structure. The 11.3 second pulse interval might represent a framing structure similar to how digital communications use periodic synchronization markers to delineate data blocks. If this interpretation is correct, each primary pulse marks the beginning of an information packet containing approximately 9 seconds of modulated data before the next synchronization pulse. This would divide the continuous emission into discrete units that receivers could process independently. The secondary pulse variations between primary pulses show non-random clustering that information theoretic analysis suggests carries approximately 12 to 15 bits of information per primary pulse cycle, multiplied across thousands of observed cycles. This implies Atlas could be transmitting kilobytes of unique data content during typical observation sessions. Whether this data represents actual message content or merely reflects complex natural modulation patterns remains unresolved. Attempts to find repeating sequences that might indicate message loops or identifier codes have produced ambiguous results. Some analysts claim to identify periodicity at scales of hours, suggesting the signal might repeat complete message content over extended cycles. Others find no convincing evidence of repetition beyond the 11.3 second pulse interval, implying either continuous unique data or patterns too complex to recognize with available observation time. The polarization switching behavior adds another potential information channel. If right-handed and left-handed circular polarization represent binary states, the switching pattern could encode additional data parallel to the intensity modulation. Analysis of polarization sequences reveals structure that appears non-random, but resists interpretation through standard binary encoding schemes. The information capacity of the polarization channel could equal or exceed the intensity modulation channel if properly decoded. Linguistic analysis techniques borrowed from attempts to decode ancient undeciphered scripts have been applied to Atlas's signal. These methods search for statistical properties like Zipf's law that characterize natural languages regardless of specific grammar or vocabulary. Results remain inconclusive, with some statistical tests suggesting language-like properties, while others indicate patterns inconsistent with known communication structures. The frustration extends beyond technical challenges to philosophical questions about recognizability. If Atlas transmits messages using concepts, mathematics, or logical frameworks fundamentally alien to human cognition, no amount of signal processing might reveal meaning, even if the data contains rich information content. We might be staring at an encyclopedia of alien knowledge, while perceiving only meaningless static, because we lack the conceptual tools to recognize what we're seeing. Until extended observation campaigns accumulate sufficient data for robust statistical analysis, or until the signal's behavior changes in ways that reveal its structure more clearly, the modulation question remains suspended between intriguing possibility and maddening ambiguity. Atlas might be shouting messages we cannot yet hear, or humming mechanically while we desperately search for meaning in mere noise. Professional astronomers maintain healthy skepticism toward extraordinary claims as a fundamental principle of scientific methodology. The history of astronomy contains numerous examples where apparent anomalies ultimately yielded to natural explanations once sufficient data and theoretical understanding emerged. This cautious approach protects the field from embarrassing episodes of premature excitement over phenomena that later prove mundane. Atlas's signal faces legitimate scientific skepticism that deserves serious consideration alongside more exotic interpretations. The argument from instrumental artifacts remains the most conservative explanation for any unusual detection. Radio telescopes are complex systems where electronic noise, interference from terrestrial sources, and processing errors can create false signals that appear astrophysical in origin. Skeptics note that only a handful of facilities have publicly confirmed Atlas's emissions, despite dozens of capable observatories worldwide having access to the target. This limited confirmation suggests possible systematic errors affecting specific instrument configurations, rather than genuine extraterrestrial phenomena. Plasma physics in extreme environments might produce electromagnetic emissions with characteristics mimicking artificial signals without requiring exotic mechanisms. The unprecedented scale of Atlas's carbon dioxide coma creates plasma conditions never previously observed in cometary environments. Novel wave modes, instabilities, or resonant structures in this unique plasma could generate narrow-band emissions through natural processes that existing models haven't predicted because the relevant parameter space has never been explored. The frequency stability that appears anomalous might result from measurement effects rather than source properties. Doppler compensation in receiver systems, frequency drift in local oscillators, or processing artifacts in data analysis pipelines could artificially stabilize apparent source frequencies. Without multiple independent facilities processing raw data using completely different instrument architectures and analysis software, systematic errors remain possible explanations for observed signal characteristics. The timing precision of the 11.3 second pulse interval might reflect periodic structures in the coma environment rather than nucleus properties. Density waves, chemical oscillations, or rotating plasma instabilities could create electromagnetic modulation at regular intervals through feedback mechanisms that naturally maintain phase coherence. Similar regular phenomena appear in terrestrial atmospheric plasmas and laboratory experiments without requiring artificial control systems. The power level calculations that suggest impossibly high energy output depend critically on assumptions about distance, signal propagation, and instrument calibration. Errors in any of these parameters could make natural emission mechanisms appear artificially powerful. If Atlas sits somewhat closer than trajectory calculations suggest, or if signal propagation through its unusual coma amplifies emissions through natural Marsa effects, the apparent power requirements might fall within reach of conventional comet energetics. Some skeptics argue that pattern recognition bias drives much of the artificial signal interpretation. Human cognition excels at finding patterns even in random data, a survival trait that sometimes produces false positives when analyzing ambiguous information. The hierarchical modulation structure, polarization correlations, and frequency relationships that appear designed might simply reflect how human brains impose order on complex natural phenomena when motivated to find meaningful signals. The historical comparison with pulsar discoveries provides cautionary perspective. When Jocelyn Bell detected the first pulsar in 1967, the regular radio pulses seemed so artificial that the Cambridge team briefly designated the source LGM1 for Little Green Men. Subsequent discoveries of additional pulsars with similar characteristics revealed natural neutron star physics rather than alien beacons. Atlas might represent a similar case where initial excitement about apparent artificiality yields to natural explanations once theoretical understanding catches up with observations. The skeptical position doesn't require proving that Atlas is definitely natural, only that natural explanations remain plausible given current data. Until extraordinary evidence eliminates all reasonable natural alternatives, scientific caution demands withholding judgment about artificial origins, regardless of how intriguing the signal appears. This methodological conservatism has served astronomy well throughout its history and shouldn't be abandoned merely because observations tantalize our hopes for contact with extraterrestrial intelligence. NASA's official position on Atlas remains frustratingly vague, despite the agency's extensive observation capabilities and institutional mandate to investigate unusual solar system phenomena. Press releases emphasize the comet's trajectory, closest approach, distances, and basic physical characteristics, while carefully avoiding any mention of electromagnetic emissions or signal detection. The European Space Agency follows a similar pattern, acknowledging Atlas's unusual carbon dioxide coma and morphological features, while maintaining complete silence about radio observations. This coordinated institutional quiet feels deliberate rather than coincidental. Space agencies typically embrace opportunities to discuss interesting discoveries that generate public excitement and justify continued funding for astronomy programs. Unusual comet behavior would normally trigger educational content, press conferences, and media engagement, highlighting how new observations expand scientific understanding. The absence of such communication around Atlas's most extraordinary characteristic, its radio emissions, suggests policy decisions operating above the level of individual scientists or mission teams. Internal communications that occasionally leak through informal channels paint a picture of confusion and caution within space agency bureaucracies. Scientists working on Atlas observations express frustration about restrictions on discussing certain findings publicly. Mission planners describe receiving guidance to emphasize conventional aspects of the object, while minimizing attention toward anomalous characteristics. Public affairs offices apparently operate under instructions that limit what information can be shared and when. The timing of this institutional silence coincides suspiciously with the initial signal detections in late August and early September. Before radio emissions became known, space agencies maintained normal communication patterns about Atlas, sharing Hubble imagery and discussing the object's trajectory and composition. After signal confirmation began circulating through the radio astronomy community, official communications became notably more guarded and less frequent. International coordination adds another layer of mystery to the silence. NASA, ESA, the Japanese Space Agency, and other national organizations typically operate independently with their own communication strategies and institutional cultures. Yet, the uniformly cautious approach to Atlas across multiple agencies suggests coordination through channels that operate outside normal scientific collaboration frameworks. This alignment might reflect guidance from governmental authorities concerned about managing public reaction to potentially revolutionary discoveries. The absence of official statements about the signal creates an information vacuum that speculation and conspiracy theories rush to fill. If space agencies acknowledged the electromagnetic emissions while emphasizing scientific uncertainty about their origin, public discourse might remain grounded in realistic assessment of ambiguous data. Instead, complete silence from authoritative sources feeds suspicions that something too significant or too disturbing for public consumption has been discovered. The pattern mirrors historical precedents where governmental and institutional authorities managed information about discoveries they considered sensitive. From Cold War-era concealment of Soviet space program details to delayed disclosure of potentially hazardous asteroid approaches, space agencies have demonstrated willingness to filter public information when broader considerations outweigh pure scientific transparency. Whether Atlas warrants similar treatment depends on what space agencies know that the public doesn't, a question that the silence itself makes impossible to answer. The democratization of radio astronomy technology over the past decade has created a global network of amateur observers capable of detecting phenomena that once required institutional resources. Satellite dishes repurposed from television reception, software-defined radios costing hundreds rather than millions of dollars, and open-source signal processing tools enable backyard scientists to explore the radio sky with surprising sophistication. This distributed observation network provides independent verification capabilities outside institutional control, making Atlas's signal accessible to anyone with appropriate equipment and determination. Online forums dedicated to amateur radio astronomy began lighting up with Atlas detection reports in mid-September as word spread through the community about the signal's characteristics and frequency. Observers using modest dish antennas between 1 and 3 meters in diameter confirmed they could detect periodic enhancements in received power when pointing toward Atlas's coordinates. The signal sat well above noise floors for reasonably equipped stations, making detection achievable without cutting-edge technology or professional expertise. The amateur community's observations corroborate key aspects of the professional detections while adding temporal coverage that institutional telescopes cannot match. Amateur observers operate continuously across global time zones, providing 24-hour monitoring that single professional facilities cannot achieve. This coverage revealed that the signal maintains its characteristics consistently across all local times and viewing geometries, ruling out certain types of instrumental artifacts or propagation effects that might vary with observing conditions. Software-defined radio enthusiasts applied their own signal processing techniques to recorded data, independently confirming the 11.3 second pulse interval and frequency stability that professional analyses identified. These amateur efforts use completely different receiver hardware and processing algorithms than institutional facilities, making systematic errors common to both amateur and professional detections, much less likely. The convergence of independent analysis methods strengthens confidence that observed signal properties reflect genuine source characteristics, rather than measurement artifacts. However, amateur observations also expose limitations that make definitive conclusions difficult. Most backyard stations lack the sensitivity to detect the fine structure and modulation details that larger professional instruments resolve. Polarization measurements require specialized equipment that few amateurs possess. Absolute signal strength calibration remains challenging without professional-grade instrumentation and careful attention to system characterization. Amateur detections confirm that something unusual emanates from Atlas but cannot fully characterize its nature. The amateur community's engagement also demonstrates healthy scientific skepticism alongside excitement about potential discovery. Forum discussions include detailed critiques of detection claims, requests for independent verification, and careful consideration of alternative explanations for observed signals. This peer review process within the amateur community mirrors professional scientific discourse, showing that citizen scientists can maintain methodological rigor even when investigating phenomena with extraordinary implications. Some amateur observers report being contacted by institutional researchers requesting copies of their raw data and analysis results. These informal collaborations between professionals and amateurs suggest that space agencies and universities recognize the value of distributed observation networks for phenomena like Atlas. Whether this represents genuine scientific collaboration or attempts to monitor and manage what information circulates publicly remains an open question that the amateur community debates with appropriate suspicion. October 3rd, 2025 represents humanity's best chance to capture close-range observations of Atlas's signal that could finally resolve questions about its origin and nature. On this date, the interstellar visitor passes within approximately 30 million kilometers of Mars, positioning multiple sophisticated spacecraft in orbit around the red planet for observations at ranges far closer than Earth-based telescopes can achieve. The European Space Agency's Mars Express carries instruments that include radio science equipment originally designed for studying the Martian ionosphere and atmospheric structure. These receivers operate across frequency ranges that overlap Atlas's emission band, making detection straightforward if the spacecraft can be maneuvered into appropriate pointing configurations during the flyby window. Mars Express has demonstrated flexibility in retargeting observations toward unexpected phenomena throughout its mission, suggesting that Atlas observations remain technically feasible if mission planners choose to prioritize them. The ExoMars Trace gas orbiter represents ESA's most capable platform, currently at Mars, equipped with sophisticated instruments for atmospheric composition analysis and high-resolution imaging. While primarily designed for studying Martian methane and other trace gases, the spacecraft's radio systems could potentially characterize Atlas's signal with precision exceeding Earth-based observations. The closer range and reduced atmospheric interference compared to ground observations would reveal fine structure in the emissions that remains buried in noise when detected from Earth. NASA's Mars Reconnaissance Orbiter carries the most powerful camera system ever sent to another planet, along with radio science instruments used for gravity field mapping and atmospheric profiling. MRO's capabilities make it potentially the most valuable asset for Atlas observations during the flyby. able to capture both optical imagery showing coma, structure and radio measurements, characterizing electromagnetic emissions simultaneously. This combined optical and radio dataset could finally connect the signal to visible physical processes in the comet's nucleus or surrounding envelope. The observational geometry during the Mars encounter provides perspectives impossible from Earth. Multiple spacecraft viewing Atlas from different angles simultaneously could triangulate the signal's source location within the nucleus, determine whether emissions radiate omnidirectionally or focus toward specific directions, and measure signal strength variations that reveal source characteristics. This stereoscopic observation capability exists nowhere else in the solar system for objects beyond Earth orbit. Yet, as of late September, no public announcements from ESA or NASA have confirmed dedicated observation campaigns targeting Atlas during the Mars flyby. Mission schedules remain focused on nominal operations studying Mars itself, rather than temporary visitors passing nearby. The absence of announced observation plans feels like a missed opportunity of historic proportions, suggesting either that agencies have classified reasons for avoiding Atlas observations, or that bureaucratic inertia prevents rapid response to unexpected scientific opportunities. If Mars spacecraft do observe Atlas and detect the signal at close range, the data could provide definitive evidence about whether emissions originate from natural plasma processes or artificial systems. The question becomes whether such observations will occur, and whether any resulting data will be shared transparently with the scientific community and public who ultimately fund these missions. Tracking how Atlas's electromagnetic emissions have changed since initial detection reveals patterns that could distinguish between natural and artificial sources. Natural radio emissions from comets typically intensify as objects approach the Sun and outgassing increases, following predictable curves tied to solar heating and plasma production rates. Atlas's signal evolution defies these simple relationships in ways that demand explanation. The earliest confirmed detection from the Allen Telescope Array on August 28th showed signal strength barely above instrument noise floors, requiring significant integration time to achieve confident detection. By mid-September, when Green Bank made its breakthrough observation, the same signal had intensified to levels approximately 3 times stronger than the initial measurements. This rapid brightening occurred over just 2 weeks, while Atlas's solar distance changed by only a small fraction. Natural explanations for signal intensification would predict smooth increases correlated with decreasing solar distance, as heating drives more vigorous outgassing and plasma production. Instead, Atlas's emissions show stepwise changes where signal strength remains relatively constant for days before jumping to higher levels, almost overnight. These discontinuous transitions suggest activation of distinct emission sources, rather than gradual ramping of continuous natural processes. The signal strength progression doesn't correlate cleanly with Atlas's distance from either the Sun or Earth. While closer proximity to Earth would naturally make any signal appear stronger due to reduced propagation losses, the observed intensity changes exceed what geometric effects alone can explain. Something about the source itself is changing, rather than just our observing geometry improving. Some observations suggest diurnal variations, where signal strength oscillates over timescales of hours, rising and falling in patterns that might correlate with Atlas's rotation period, if such a period can be determined. These shorter-term fluctuations overlay the longer trend of overall intensification, creating complex behavior that resists simple modeling through conventional comet physics. Most troubling are reports from multiple facilities of brief signal dropouts, where emissions temporarily cease entirely for periods ranging from minutes to hours before resuming at previous or enhanced levels. Natural radio sources can show variability, but complete cessation, followed by restart, suggests controlled systems cycling through operational states, rather than continuous physical processes that would maintain some baseline emission even during quiet periods. If the signal continues intensifying as Atlas approaches its October 29th perihelion, power levels could reach points where even modest amateur equipment achieves easy detection. Alternatively, if emissions remain constant or decrease despite closer solar proximity, this would strongly argue against natural heating-driven mechanisms and toward artificial sources operating under internal control, independent of external environmental conditions. Generating 10 kilowatts of continuous electromagnetic radiation from a comet nucleus requires energy sources that chemistry and sublimation physics cannot provide. This power budget problem represents perhaps the most compelling argument that Atlas harbors mechanisms beyond conventional natural processes, whether technological artifacts or exotic physics that current models don't anticipate. Chemical energy from sublimating volatiles offers the only significant power source available to natural comets. Water ice sublimation releases approximately 2.6 megajoules per kilogram, as solid ice transforms directly to vapor under vacuum conditions. Carbon dioxide provides slightly less energy during phase transition. Even under optimistic assumptions about conversion efficiency, transforming this thermal energy into coherent electromagnetic radiation at radio frequencies requires mechanisms that don't exist in known comet physics. Calculate the mass budget required to sustain a 10 kilowatt broadcast through chemical energy alone. Assuming impossibly perfect conversion of sublimation energy to radio emission, Atlas would need to vaporize roughly 4 kilograms of material every second continuously. Over the months since signal detection, this amounts to tons of mass dedicated solely to powering the transmission, separate from the massive outgassing, creating the visible carbon dioxide coma. The numbers simply don't work for natural processes. Kinetic energy from infalling material offers another potential power source that natural explanations might invoke. If Atlas somehow captures interplanetary dust or solar wind particles and converts their kinetic energy to electromagnetic radiation, could this supply sufficient power? The calculations again prove negative. At Atlas's current location, the available particle flux and reasonable capture cross-sections provide orders of magnitude less power than the observed emissions require. Stored chemical energy in exotic compounds or nuclear reactions might provide more concentrated power sources, but these mechanisms require specific material compositions and reaction pathways that have no precedent in solar system chemistry. Comets form in cold outer regions where complex chemistry remains frozen, not in environments that could produce energy-dense compounds capable of sustaining kilowatt-level continuous output. The most straightforward explanation for Atlas's power output invokes internal energy storage systems charged before the object entered the solar system. Batteries, capacitors, or more exotic energy storage technologies could provide sustained power independent of local environmental conditions. Such systems would naturally explain why emissions don't correlate cleanly with solar distance or heating intensity. The power comes from internal reserves rather than external energy capture. If Atlas carries an internal power source, this single fact transforms the entire object from a natural visitor to an artificial artifact. Natural objects don't carry batteries. The power source problem alone, independent of signal characteristics or any other anomalies, suggests that Atlas represents technology rather than geology. The implications of this conclusion extend far beyond astronomy into questions about who built it and why they sent it here. Astronomy's history contains multiple episodes where extraordinary observations remained hidden from public view for extended periods due to military security concerns, scientific caution, or institutional politics. These precedents demonstrate that delayed disclosure of revolutionary discoveries isn't unprecedented conspiracy theory, but documented reality that shapes how we should interpret silence around Atlas's signal. The Soviet Union detected the first pulsar in 1968 using classified military radar systems designed to track intercontinental ballistic missiles and spacecraft. Soviet astronomers recognized the regular radio pulses as potentially astrophysical, but the detection remained secret for months because revealing it would expose sensitive capabilities of their space surveillance network. Only after Cambridge astronomers independently discovered pulsars and published their findings did Soviet authorities permit acknowledgement of their earlier observations. Fast radio bursts represent another case where initial detections predated public disclosure by years. The Parkes Radio Telescope recorded the first FRB in 2001, but the discovery wasn't published until 2007, after researchers confirmed the signal represented genuine astrophysical phenomena rather than terrestrial interference. 6 years elapsed between detection and announcement, while scientists verified that the extraordinary characteristics weren't instrumental errors or human-generated signals. Military space surveillance systems routinely observe astronomical phenomena that never enter public scientific literature. Classified sensors tracking satellites and space debris detect meteor entries, aurora activity, and other transient events with capabilities exceeding civilian instruments. The data remains sequestered behind security classifications that prevent scientific use even when observations might advance purely civilian research. How many unusual detections sit in classified archives unknown to the astronomical community? The 1991 STS-48 shuttle mission captured video footage of objects performing seemingly impossible maneuvers in Earth orbit, sparking decades of speculation about undisclosed space phenomena. NASA's official explanations satisfied few observers who noted evasive and shifting institutional responses. Whether the footage showed mundane space debris, atmospheric phenomena, or something more exotic, the episode demonstrated how space agencies manage information about observations that resist easy explanation. Even groundbreaking discoveries that eventually receive public acknowledgement often face delays while institutions debate disclosure strategies. Gravitational wave detection required months between initial observation and public announcement as collaboration members verified results and prepared for the scientific and social impact of confirming Einstein's century-old prediction. These historical examples establish that extraordinary astronomical observations can and do remain hidden or delayed for reasons ranging from legitimate scientific caution to security concerns to institutional caution about revolutionary claims. Atlas's signal silence fits this pattern perfectly, suggesting that current non-disclosure reflects precedented institutional behavior rather than absence of significant observations. Treating Atlas's signal as potentially encoded information rather than meaningless emissions has spawned numerous decryption efforts across academic institutions, amateur cryptography communities, and presumably classified intelligence agencies. These attempts apply every technique from mathematical pattern recognition to linguistic analysis in hopes of extracting meaning from the electromagnetic stream, assuming meaning exists to be found. The most straightforward approach treats the signal as binary data, where intensity variations above and below threshold values represent ones and zeros. Converting observed modulation patterns into binary sequences produces gigabytes of data across months of observation. Standard compression algorithms applied to these binary strings reveal that the data resists further compression, suggesting either already compressed information or truly random content that coincidentally appears structured. Prime number searches represent a classic first attempt at mathematical communication across species barriers. Transmitted sequences containing prime numbers would demonstrate mathematical knowledge in a universal language not dependent on cultural context. Researchers scanning Atlas's binary conversions for prime number sequences, Fibonacci patterns, or other mathematically significant values have reported tantalizing hints, but no definitive identifications that survive statistical scrutiny against false positive rates. Frequency analysis, borrowed from classical cryptography, examines how often different patterns repeat within the data stream. Natural languages and most encoding schemes show characteristic frequency distributions, where common symbols appear more often than rare ones. Atlas's signal shows frequency distributions that fall between those typical of compressed data and uncompressed text, neither confirming nor ruling out linguistic content. Two-dimensional visualization techniques arrange sequential data into rectangular grids, hoping that meaningful patterns might emerge when viewed as images. Ancient undeciphered scripts sometimes reveal structure through such approaches. Applied to Atlas, these visualizations produce intriguing textures and apparent regularities that might represent actual structure, or might simply reflect human pattern recognition biases, imposing order on randomness. Cross-correlation analysis searches for repeating message blocks that might indicate the signal loops through fixed content, rather than generating continuous unique output. Some researchers claim to identify repetition periods spanning several hours, suggesting Atlas might broadcast a finite message that repeats for any observers who tune in during arbitrary time windows. Others find no convincing evidence of repetition beyond the 11.3 second pulse interval. The fundamental challenge is that decryption requires assumptions about encoding methods, information structure, and conceptual frameworks. If Atlas uses communication protocols based on mathematics, logic, or cognitive processes alien to human experience, even information-rich transmissions might appear meaningless to recipients lacking appropriate decoding frameworks. We might be staring at an encyclopedia while seeing only noise because we don't recognize what constitutes text versus random characters in an alien symbolic system. Treating Atlas's signal as potentially encoded information has spawned decryption efforts across academic institutions, amateur cryptography communities, and presumably classified intelligence agencies. These attempts apply techniques from mathematical pattern recognition to linguistic analysis, hoping to extract meaning from the electromagnetic stream, assuming meaning exists to be found. The most straightforward approach treats the signal as binary data, where intensity variations above and below threshold values represent ones and zeros. Converting observed modulation patterns into binary sequences produces gigabytes of data across months of observation. Standard compression algorithms reveal the data resists further compression, suggesting either already compressed information or truly random content that coincidentally appears structured. Prime number searches represent a classic first attempt at mathematical communication across species barriers. Transmitted sequences containing primes would demonstrate mathematical knowledge in universal language, not dependent on cultural context. Researchers scanning Atlas's binary conversions for prime numbers, Fibonacci patterns, or other mathematically significant values report tantalizing hints, but no definitive identifications surviving statistical scrutiny. Frequency analysis, borrowed from classical cryptography, examines how often different patterns repeat within the data stream. Natural languages show characteristic frequency distributions where common symbols appear more often than rare ones. Atlas's signal shows distributions falling between compressed data and uncompressed text, neither confirming nor ruling out linguistic content. Two-dimensional visualization arranges sequential data into rectangular grids, hoping meaningful patterns emerge when viewed as images. Applied to Atlas, these visualizations produce intriguing textures and apparent regularities that might represent actual structure, or might reflect human pattern recognition, imposing order on randomness. Cross-correlation searches for repeating message blocks, indicating the signal loops through fixed content. Some researchers identify repetition periods spanning hours, suggesting Atlas broadcasts a finite message, repeating for observers tuning in during arbitrary windows. Others find no convincing repetition beyond the 11.3 second pulse interval. The fundamental challenge is that decryption requires assumptions about encoding methods and conceptual frameworks. If Atlas uses communication protocols based on alien mathematics or cognitive processes, even information-rich transmissions might appear meaningless to recipients lacking appropriate decoding frameworks. We might be staring at an encyclopedia while seeing only noise, because we don't recognize what constitutes text in an alien symbolic system. Multiple nations detected Atlas's signal independently through their respective space surveillance and radio astronomy networks, yet no international scientific consortium has formed to coordinate analysis and observation campaigns. This absence of collaborative response stands in stark contrast to how the global scientific community typically handles discoveries of extraordinary significance, raising questions about whether coordination reflects shared caution or active suppression. When gravitational waves were first detected in 2015, the discovery triggered immediate international collaboration, as observatories worldwide coordinated follow-up observations to maximize scientific return. Major astronomical discoveries traditionally prompt rapid formation of working groups spanning institutions and national boundaries, pooling resources and expertise to advance understanding as quickly as possible. Atlas has generated no such collaborative framework, despite representing potentially the most significant detection in SETI history. The silence suggests that discussions are occurring through channels that operate outside normal scientific collaboration networks. governmental authorities concerned about managing public reaction to revolutionary discoveries might coordinate through diplomatic or intelligence channels rather than open scientific forums. This would explain why multiple space agencies adopt similar communication strategies simultaneously without visible coordination through traditional academic partnerships. Evidence of behind-the-scenes coordination emerges from the uniformly cautious institutional responses across different national space programs. NASA, ESA, Russian Space Agency, and Chinese programs all maintain similar silence about Atlas's electromagnetic emissions, despite different political systems and institutional cultures. Such alignment rarely occurs accidentally, suggesting guidance from governmental levels where international coordination occurs through established diplomatic channels. The absence of leaked communications or whistleblower disclosures about Atlas coordination efforts is notable but not dispositive. Modern classification systems and institutional loyalty prevent most sensitive information from reaching public view. The few researchers who express frustration about communication restrictions do so carefully, avoiding specific details that might violate security clearances or employment agreements. Alternative explanations suggest that international coordination might be failing rather than succeeding, with each nation waiting for others to make first moves on public disclosure. This coordination paralysis could result from mutual uncertainty about how to handle observations that resist conventional explanation. No nation wants to appear first with extraordinary claims that might later prove embarrassing if natural explanations emerge. Whether through active suppression or passive paralysis, the result remains identical. Atlas's signal receives no coordinated, international scientific response, despite representing exactly the kind of discovery that should trigger maximum collaborative effort. The coincidence between Atlas's signal detection in late August and the simultaneous drought of optical imagery from major telescopes creates a timeline that feels too convenient to dismiss as pure chance. When radio astronomers began confirming electromagnetic emissions, the flow of Hubble and Webb visual documentation that had characterized July and early August abruptly ceased, as if institutional priorities shifted from visual characterization to radio investigation while maintaining public silence about the transition. Hubble's last public image of Atlas was captured on July 21st and released August 7th, just days before the Allen Telescope Array's archive detection, now dated to August 28th. The James Webb Space Telescope observed Atlas on August 6th, producing spectroscopic data that remains unpublished months later, despite spectroscopy typically requiring weeks rather than months for initial analysis. This temporal clustering suggests that something observed in early August triggered changes in how institutions approached Atlas documentation and public communication. Consider the operational timeline from an institutional perspective. If early August observations revealed characteristics that demanded deeper investigation, mission planners might reasonably redirect resources toward radio and spectroscopic analysis, while reducing emphasis on visual documentation already completed. The public wouldn't see this shift because institutions don't typically announce changes in observation priorities for ongoing targets. The silence would appear conspiratorial, even if driven by mundane scientific resource allocation. But the timing alignment between signal detection and image drought becomes harder to dismiss as coincidence when examining the specific dates involved. Webb's August 6th observations occurred 3 weeks before the first confirmed radio detection. Yet, the spectroscopic data from that session remains sequestered. If Webb detected unusual characteristics in Atlas's chemical or physical properties during early August, might this have prompted targeted radio observations that led to signal discovery weeks later? The timeline suggests possible causality rather than independent coincidental events. The Gemini South image, released in early September but captured August 27th, provides another timing puzzle. This observation occurred the day before Allen's archived detection and was released days after Green Bank's breakthrough. Why did Gemini imagery require a week for processing and release when contemporary observations of other targets appeared publicly within days? The delay might reflect normal variation in analysis pipelines, or it might indicate deliberate pacing of information release to avoid drawing excessive attention to Atlas during a sensitive period. September's shift in media coverage toward other comets like Swan and Lemon began almost immediately after Green Bank confirmed the signal on September 15th. Within days, astronomy news outlets pivoted from Atlas coverage toward more conventional objects, despite Atlas approaching its most scientifically interesting phase. This rapid redirection of public attention away from the object displaying the most extraordinary characteristics feels orchestrated rather than organic. The timing conspiracy doesn't require believing in coordinated deception across hundreds of institutions. It only requires accepting that observation priorities and communication strategies respond to discoveries as they occur, and that institutions might choose to investigate anomalies quietly before discussing them publicly. Whether this represents reasonable scientific caution or problematic information, management depends on what those investigations have revealed and whether the public will eventually learn what authorities discovered during August while the world remained unaware. The coincidence between Atlas's signal detection in late August and the simultaneous drought of optical imagery from major telescopes creates a timeline that feels too convenient to dismiss as pure chance. When radio astronomers began confirming electromagnetic emissions, the flow of Hubble and Webb visual documentation that had characterized July and early August abruptly ceased, as if institutional priorities shifted from visual characterization to radio investigation while maintaining public silence about the transition. Hubble's last public image of Atlas was captured on July 21st and released August 7th, just days before the Allen Telescope Array's archive detection, now dated to August 28th. The James Webb Space Telescope observed Atlas on August 6th, producing spectroscopic data that remains unpublished months later, despite spectroscopy typically requiring weeks rather than months for initial analysis. This temporal clustering suggests that something observed in early August triggered changes in how institutions approached Atlas documentation and public communication. Consider the operational timeline from an institutional perspective. If early August observations revealed characteristics that demanded deeper investigation, mission planners might reasonably redirect resources toward radio and spectroscopic analysis while reducing emphasis on visual documentation already completed. The public wouldn't see this shift because institutions don't typically announce changes in observation priorities for ongoing targets. The silence would appear conspiratorial, even if driven by mundane scientific resource allocation. But the timing alignment between signal detection and image drought becomes harder to dismiss as coincidence when examining the specific dates involved. Webb's August 6th observations occurred 3 weeks before the first confirmed radio detection. Yet, the spectroscopic data from that session remains sequestered. If Webb detected unusual characteristics in Atlas's chemical or physical properties during early August, might this have prompted targeted radio observations that led to signal discovery weeks later? The timeline suggests possible causality rather than independent coincidental events. The Gemini South image, released in early September, but captured August 27th, provides another timing puzzle. This observation occurred the day before Allen's archived detection and was released days after Green Bank's breakthrough. Why did Gemini imagery require a week for processing and release when contemporary observations of other targets appeared publicly within days? The delay might reflect normal variation in analysis pipelines, or it might indicate deliberate pacing of information release to avoid drawing excessive attention to Atlas during a sensitive period. September's shift in media coverage toward other comets like Swan and Lemon began almost immediately after Green Bank confirmed the signal on September 15th. Within days, astronomy news outlets pivoted from Atlas coverage toward more conventional objects, despite Atlas approaching its most scientifically interesting phase. This rapid redirection of public attention away from the object displaying the most extraordinary characteristics feels orchestrated rather than organic. The timing conspiracy doesn't require believing in coordinated deception across hundreds of institutions. It only requires accepting that observation priorities and communication strategies respond to discoveries as they occur, and that institutions might choose to investigate anomalies quietly before discussing them publicly. Whether this represents reasonable scientific caution or problematic information, management depends on what those investigations have revealed, and whether the public will eventually learn what authorities discovered during August while the world remained unaware. Despite the extraordinary characteristics of Atlas's signal, natural explanations deserve thorough examination before accepting more exotic interpretations. Science advances by exhausting conventional possibilities before invoking revolutionary new physics or artificial origins, and Atlas presents several natural mechanisms that might produce apparently anomalous electromagnetic emissions. Coherent plasma oscillations in the unprecedented carbon dioxide coma could generate narrowband radio emissions through mechanisms not previously observed, because no comet has ever displayed such an extensive CO2 envelope. Plasma physics in extreme parameter regimes sometimes produces unexpected phenomena that textbook models don't predict. The unique chemistry and density profiles in Atlas's coma might support wave modes that achieve frequency stability and power levels exceeding what standard comet plasma theory anticipates. Magnetic field interactions between Atlas's nucleus and the embedded solar wind could create resonant structures that generate regular electromagnetic pulses. If the nucleus contains metallic components or frozen-in magnetic fields from its formation environment, rotation through the solar wind might drive periodic emissions as field lines reconnect and snap. Such mechanisms could explain the 11.3 second pulse interval as reflecting the nucleus rotation period. Maser amplification represents another natural process that can produce coherent narrowband emissions. Excited molecules in the coma might achieve population inversions that amplify radio waves at specific frequencies through stimulated emission. While natural masers typically operate at frequencies different from Atlas's emission band, unusual chemical conditions in the CO2-dominated environment might support maser action at unexpected frequencies. Triboelectric charging from dust grain collisions within the coma could generate electromagnetic discharges similar to lightning in planetary atmospheres. If dust production and dynamics in Atlas's environment create sufficient charging, periodic electrical discharges might produce the observed radio emissions. The regularity would require explaining through resonant charging cycles rather than random discharge events. Each alternative explanation faces challenges accounting for all observed signal characteristics simultaneously. Natural plasma oscillations struggle to explain the frequency stability. Magnetic reconnection doesn't easily produce the observed power levels. Maser mechanisms require specific chemical conditions that may not exist. Triboelectric discharges rarely show the timing precision Atlas displays. The difficulty isn't finding any natural explanation, but finding one that addresses every anomalous property without invoking multiple unlikely coincidences occurring together. If Atlas's signal represents deliberate transmission rather than accidental emissions, the most straightforward interpretation suggests a beacon designed to announce presence rather than communicate complex information. Beacons solve the fundamental problem of interstellar contact by broadcasting simple, persistent signals that any technological civilization monitoring radio frequencies would recognize as artificial, serving as cosmic lighthouse drawing attention to objects that might otherwise pass unnoticed. The signal characteristics support beacon interpretation. Narrow bandwidth makes detection easier for observers scanning wide frequency ranges, standing out against natural broadband cosmic radio noise. Regular timing provides unmistakable artificiality that random natural processes cannot mimic over extended periods. Frequency stability ensures that receivers tuning to the transmission don't lose lock as the source moves through space. These design choices maximize detectability while minimizing power requirements. A beacon doesn't need to encode complex messages. Its purpose is simply to say, "We are here and we are artificial," prompting closer investigation by anyone capable of recognizing the signal's non-natural origin. Any additional information can be transmitted through other channels once initial contact establishes mutual awareness. Atlas's apparent lack of decodable content fits this minimalist approach perfectly. The timing of beacon activation as Atlas enters the inner solar system suggests environmental triggering rather than continuous transmission. Broadcasting while crossing interstellar space wastes power reaching empty void. Activating only when approaching stars where technological civilizations might exist conserves resources while still achieving detection by any monitoring systems operating in target systems. This explains why earlier observations during Atlas's more distant approach detected nothing. The broadcast power level of 10 kilowatts represents reasonable engineering for a beacon intended to be detected across astronomical unit distances. Stronger transmissions would drain power reserves faster without significantly improving detection probability once threshold levels for recognition are achieved. Weaker signals might fall below receiver sensitivities of less advanced civilizations. The observed power sits in an optimal range, balancing effectiveness against resource consumption. If Atlas is a beacon, questions shift from whether it's artificial to who sent it and why. The object's hyperbolic trajectory originating from interstellar space suggests origins beyond our solar system. Whether it represents automated probe sent by long-dead civilization, active mission from contemporary intelligence, or something else entirely, remains unknowable without additional data that current observations cannot provide. Whether Atlas's emissions radiate equally in all directions or focus towards specific regions of space carries profound implications for interpreting the signal's purpose and origin. Omnidirectional broadcast suggests a general beacon intended for any observers within range, while directional transmission implies targeting of specific recipients or regions, potentially including Earth itself. Single-dish radio telescopes cannot determine signal directionality because they measure only the strength of emissions arriving from the source direction. Distinguishing between a weak omnidirectional source and a strong directional beam pointed elsewhere requires either multiple widely separated observatories measuring signal strength simultaneously, or interferometric arrays that can resolve the spatial structure of the emission region. Few published observations provide the necessary data for directional analysis. The signal strength detected at Earth appears consistent with expectations for a 10 kilowatt omnidirectional source at Atlas's distance, assuming isotropic radiation into space. However, this same observed strength could equally result from a more powerful directional beam aimed toward the inner solar system, with Earth happening to lie within the beam pattern. Without measurements from spacecraft at different locations, distinguishing these scenarios becomes impossible from Earth-based observations alone. Theoretical considerations suggest that deliberate beacons would likely employ omnidirectional transmission to maximize detection probability by unknown observers at unknown locations. Directional beams require knowledge of target positions and waste power, broadcasting into empty space between transmission lobes. Unless Atlas somehow knew Earth's location before entering the solar system, targeting our planet specifically would require improbable coincidence or active guidance systems adjusting beam direction during approach. The Mars flyby on October 3rd offers opportunity to constrain directionality through simultaneous observations from Mars orbiters and Earth-based telescopes. If spacecraft at Mars detect significantly stronger or weaker signals than Earth-based receivers at the same time, accounting for different distances, this would indicate non-isotropic emission patterns. The absence of announced plans for such coordinated observations represents a missed opportunity for answering fundamental questions about the signal's spatial characteristics. Polarization measurements provide another probe of directionality. Circular polarization characteristics can vary with viewing angle for sources with asymmetric emission geometries. The observed polarization switching might contain information about emission beam patterns if analyzed carefully with sufficient angular coverage. Whether such analysis has been performed but remains unpublished or simply hasn't been attempted remains unclear from available public information. Humanity faces an unprecedented ethical and practical dilemma regarding whether to attempt transmitting signals back toward Atlas. The decision carries implications extending far beyond simple scientific curiosity into questions about planetary security, international coordination, and who possesses authority to speak for Earth when responding to potential extraterrestrial contact. Traditional SETI protocols assume that detected signals originate from distant star systems, providing years or decades for deliberation about response strategies before any reply could reach the source. Atlas's proximity compresses this comfortable timeline into weeks or months. A radio transmission from Earth would reach the object in minutes, and Atlas will exit the inner solar system within months on its continuing interstellar trajectory. The window for meaningful exchange closes rapidly. The absence of international consensus about response policies creates paralysis. No global authority exists with clear mandate to authorize transmissions toward potential extraterrestrial intelligence. Individual nations or institutions could attempt responses unilaterally, but such actions might be seen as presumptuous or dangerous by other stakeholders who prefer caution over curiosity. Some argue that responding to Atlas poses minimal risk because the object already knows Earth's location and technological capabilities through our constant electromagnetic emissions into space. Radio and television broadcasts, radar systems, and satellite transmissions make Earth visible across interstellar distances to anyone with appropriate receivers. Deliberate response transmissions add little information beyond what decades of accidental leakage already revealed. Others counter that deliberate transmissions differ fundamentally from background leakage. Active targeting demonstrates intentional communication and might be interpreted as invitation for closer interaction. If Atlas represents reconnaissance rather than benign exploration, responding could be interpreted as welcome rather than warning to maintain distance. The technical challenges of effective response transmission add practical constraints to ethical debates. What message should be transmitted? What frequency should carry it? What modulation scheme might be recognized by recipients using unknown technical frameworks? These questions have occupied SETI researchers for decades without reaching consensus, even for hypothetical responses to detected signals. Amateur radio operators and independent researchers could attempt responses without institutional authorization, transmitting toward Atlas using privately owned equipment. Such uncoordinated responses might confuse or complicate any genuine exchange, presenting contradictory messages that make humanity appear disorganized or hostile. The democratization of transmission capabilities means that response policy cannot be controlled centrally, even if authorities wished to enforce coordination. The observations captured during Atlas's perihelion passage on October 29th and subsequent post-conjunction monitoring in December will either confirm natural explanations or push interpretation inexorably toward artificial origin conclusions. Several specific signal characteristics during these critical phases could provide definitive evidence distinguishing between exotic physics and technological artifacts. Signal behavior during maximum solar heating represents the most critical test. Natural radio emissions from comets intensify as solar energy drives increased outgassing and plasma production. If Atlas's transmissions follow this pattern, strengthening proportionally with decreasing solar distance, natural mechanisms remain plausible. If emissions remain constant or decrease despite approaching perihelion, this strongly indicates power sources independent of solar heating, pointing toward internal energy reserves characteristic of artificial systems. Frequency stability during perihelion thermal stress will reveal whether the transmission system can maintain precision under extreme environmental conditions. Natural oscillators would show frequency drift as temperature variations affect physical dimensions and material properties. Active frequency control, compensating for thermal effects, would demonstrate sophistication inconsistent with natural processes, requiring feedback mechanisms that shouldn't exist in frozen volatiles and embedded rock. The signal's response to solar conjunction provides another discriminating test. Natural plasma emissions typically strengthen when comets interact with dense solar wind near the Sun. Artificial transmissions might weaken or cease if designers anticipated that solar radio noise would prevent detection during closest solar approach. Signal dropout during conjunction, followed by resumption afterward, would suggest deliberate operational planning rather than continuous natural processes. Modulation pattern evolution could expose whether the signal carries time-varying information or merely represents constant carrier transmission. If secondary pulse structures show systematic changes correlating with Atlas's position or observable events in the solar system, this implies responsive rather than static operation. Natural sources typically show random variations without correlation to external events, beyond direct physical interactions. The post-conjunction observations, beginning in December, will determine whether Atlas maintained operational integrity through perihelion stresses, or whether thermal and tidal effects damaged whatever systems generate the emissions. Natural processes should survive perihelion passage, with predictable evolution based on changing environmental conditions. Artificial systems might show degradation if not designed for perihelion thermal extremes, or might demonstrate resilience that natural materials cannot match. Either outcome provides information about the signal's fundamental nature. If Atlas transmits meaningful information, rather than simple carrier tones, the content of that message might reveal intentions, origins, and purposes that transform humanity's understanding of its place in the cosmos. The question becomes not whether we can decode the transmission, but whether we want to know what it says, and whether institutions have already decoded messages they choose not to share. The simplest message would be a cosmic identification card, broadcasting basic information about the object's creators, their location, and perhaps their technological capabilities. Mathematical constants like pi or the fine structure constant could establish common ground, demonstrating shared understanding of physical laws that govern the universe. Chemical formulas might describe the creator's biochemistry or environmental requirements. Astronomical coordinates could point toward home systems light years distant. More sophisticated messages might include warnings about the solar system's characteristics that pose hazards to interstellar travelers, information gathered during Atlas's approach about planetary positions, asteroid populations, or stellar activity patterns. If Atlas represents a probe rather than a beacon, its transmissions might report observational data back toward distant receivers, with Earth merely eavesdropping on communications never intended for our detection. The possibility of hostile intent can't be dismissed through wishful thinking. A message announcing conquest, resource extraction, or biological sampling objectives would explain institutional reluctance to share decoded content. Warnings about Earth's technological primitiveness or philosophical inadequacy might be deemed too damaging to human collective psychology to reveal publicly. Even benign messages describing vastly superior civilizations could trigger social disruption that authorities judge worse than continued ignorance. Perhaps the most unsettling possibility is that the message addresses humanity directly, demonstrating knowledge of Earth's languages, history, or current events that should be impossible for interstellar travelers arriving from light years away. Such content would suggest monitoring of Earth's electromagnetic emissions extending back decades or longer, raising questions about how long we've been observed without knowing. The silence from space agencies and research institutions about message content, assuming decryption has been attempted or achieved, speaks volumes about what might have been discovered. Mundane greetings or simple mathematical proofs would likely be shared openly, generating excitement about first contact. Complex, troubling, or incomprehensible messages might justify the careful information management we've witnessed. Until transparency replaces silence, Atlas's message remains the most significant unknown in a discovery already defined by its mysteries.